Okay, so the next speaker will be Piotr Kolenderski, who will speak about experiments on quantum communication and clock synchronization with single photons.
Okay, hello everybody. So first of all, I would like to thank the organizers for letting me to present my work here. So I came from Nicolaus Copernicus University, at which we have National Laboratory of Atomic, Molecular and Optical Physics. And this is a bigger laboratory which consists of many laboratories. So one of them is Single Photon Application Laboratory. So this is where I work. And okay, does it work? Okay. So the work that I'm presenting here has been done with collaboration with my postdoc and my PhD student who work with me in Torun. So what is the closer? Is it any better? No? Yeah? Okay, so what's the motivation? So the motivation is the following. Let's imagine that we have a source of single photons. We have a channel, a transmission channel. In my case, that's going to be a single mode fiber, and on the other end of that fiber, there is another party who wants to detect the signal. So I want, for example, to transmit an information, or I want to synchronize two clocks. One is here, the other is here. So the main question is, how can we do that effectively or efficiently? So single mode fibers or fibers in general are very well developed, so we don't actually do anything about the channel. So the channel is fixed, that's the single mode fiber. So we want to play a little bit with the detector and the source itself in order to make it optimal, make it better. Okay, so what do we want to do? We want to maximize the transmission distance, and we want to synchronize remote clocks. So that's going to be two things in one scenario. I'm going to stick a little bit more to quantum communication in order to explain the idea. So why do we want to play with sources and detectors? Because all of those three elements are not perfect. So for example, the transmission channel has its own losses, and there's dispersion, which gives the limit of the distance of communication. So let's take a look at the detector side. So detectors, they are also not perfect. So they feature dark counts. There is a timing jitter, which gives the limit for the precision of the detection time. And there is also quantum efficiency, so which is lower than unity in general. So what can we do in order to extend the transmission distance? So we can apply a technique which is called temporal filtering. So let's assume that this is the wave packet which describes the photon that is being transmitted in the fiber in the channel. So we can open the detector for a certain time, but the longer this detection window is, the better the chances that we get more dark counts. So the dark count rate is proportional to this detection window. So the longer, the worse. So we can adjust the detection window such that it's as short as possible. So we can narrow down to, let's say, 3 sigma, where sigma is the standard deviation of the wave packet here. So then there's 99% of this wave packet in that detection window. So this is classical. And that's it, right? But we can do something more. We can use quantum correlations in temporal domain, or as you wish, in spectral domain, in order to narrow down this detection window even more. So as I will show, we can, within my scenario, we can reduce that to 30% of the original detection window. So what would be the consequence? Actually, we will lower the dark count rate, and we will increase the signal to noise ratio. Okay, so what is the implementation? The implementation is simple. So In the middle, we have a parametric down conversion source. We have two channels. These are long single mode fibers. And there is Alice and Bob, as always. And they have single photon detectors with electronics, which allows them for time stamping. So they have time resolved measurements at hand. They also have a classical communication channel that they can use if they want. Okay, so what's the goal here? The goal is to perform quantum key distribution, as an example, as far as we can. Okay, so let's briefly say something about SPDC. So this is a process which takes place in a nonlinear crystal. So if you have a very strong pump beam, then from time to time, one of the photons in the nonlinear crystal decays spontaneously into a pair of photons. So this photo is very specific. So it took around 2 minutes to take that photo. Usually you don't see that in the lab. Okay, so what is the resource that we want to use in order to make it happen, to extend the range of, let's say, quantum communication? So typically, one photon decays into a pair. So we couple that pair into single mode fibers, and usually that pair can feature polarization, spectrals, or spatial entanglement, or a combination of these three. We will use polarization entanglement in order to perform a QKD. So this is a classic scenario. And we use spectral entanglement in order to extend the distance. So there is no spatial entanglement in our case because we couple to single mode fibers. So this is separable state in this degree of freedom. Okay, so we have to analyze a little bit more or go into details a little bit more about spectral entanglement. So there is one number that can say what is the type of spectral entanglement. So this row here says about the degree of entanglement that we have in a pair of photons. So let's say if I say that the spectral entanglement is negative, then it means that a photon with the higher energy on one, okay, so let's say higher energy photon here with the lower energy photon here are correlated and vice versa. So this is the negative spectral correlation. If there is no correlation, then rho is 0. And if there is positive correlation, meaning that the frequencies of the correlated photon coincide, then we say that the correlation is positive. So this is not against energy conservation relation because you can get this case only if you have a pulsed pump beam. Okay, so example number 1. Let's consider this scenario that I briefly described before. So we use polarization entanglement for QKD and spectral entanglement to increase the distance. So as I will show in a few minutes, the stronger the spectral correlation, the narrower the wave packet. So we want to work on spectral correlation to make it as strong as possible in order to have the wave packet at both sides as narrow as possible. So the scenario is such that Alice measures a photon, so we can think that the event of detection here heralds a photon at both sides. And based on this information, Alice and Bob also, they know that the wave packet was narrower compared to the situation that there was no information about detection on Alice's side. So the time resolved measurement is actually essential for this technique. Okay, so we applied this idea for QKD. So in QKD, you consider key generation rate. So this is the amount of secure key on the unit of time that you can get. And here, this is a logarithm of key generation rate, and this is the distance between Alice, actually half of the distance between Alice and Bob. So this is the length of the fiber. So as you can see, the longer the fiber, the lower the key generation rate. So let's say we can set our limit at -8, and we can compare different scenarios. So as I will show you in a few moments, my source can generate any type of entanglement. So we analyzed what is going to happen if we change the sign or we change the value of spectral correlation. So if we use photons, a pair of photons, which are negatively correlated, so let's say we have the limit of the distance, which is below 160 kilometers. So if we switch our source to the mode such that it generates no entanglement or the correlated photons, then we can extend that limit a little bit. But if we switch to positive correlation, then we can do much better. We can increase that distance by 20 kilometers. So we can imagine existing QKD setup that you can improve by using this kind of source. So there is existing setup. You just use this source, and then you increase by 20 kilometers the maximal distance, or you can improve the key generation rate with the same distance. Okay, there is one more thing. If we have additional information about global time reference, then we can even improve that distance a little bit more. So those dashed lines correspond to the case that we have, that Alice and Bob have global time reference. So that's going to be even more than 180 kilometers. And this is just a simulation, and this is just an example. Okay, so example number 2 of our idea. So let's assume that the source is in Alice's laboratory, and the link is here. So we are considering only the link between Alice and Bob. So this is our link. And now the question is, what is the optimal fiber length on Alice's side, such that for a given distance between Alice and Bob, the key generation rate is the highest. So we don't optimize right now. We are not optimizing this distance. We are optimizing the key generation rate by looking at the optimal fiber length in Alice's laboratory. Okay, so at the beginning, one could say that the shortest, the better, but it's not the case, because we have to use time result measurements, and actually dispersion in this case is our friend. So usually people who work in telecom business, they hate dispersion, and here the dispersion is really good for that, because let's consider that the distance between Alice and Bob is 197 kilometers. So this is the Alice's single-mode fiber length. So if this is too short, there is no way that key generation rate can be any good. So if this is too if this is too long, the key generation rate is also very small. So there is only a certain range in which the key generation rate is significant. So actually, for this case, we want to sit here at roughly 100, maybe 20 kilometers. So that was a little bit surprising at some point. Okay, and now let's describe the experimental setup in which we showed how the idea works. So we use a pulsed laser at 775 nanometers. We pump a regular PPKTP type 2 crystal. This dichroic mirror we use to separate the pump and the output photons. And actually the pump is monitored with a photodiode. This is our global time reference. And the output photons are separated on a polarizing beam splitter, and they are coupled to fibers. And actually these are those two fibers that we are using. The other ends of those two fibers, they are monitored by superconducting single photon detectors, which can convert a photon into electric pulse. And those electric pulses from SPDs and photodiode we analyze with an oscilloscope. Actually, we use oscilloscope as a time tagger, so it gives us the timing information about the direction here. So in practice, it looks like this. So the pump comes here. This is the PPK-TP crystal on the homemade oven. This is the photodiode, PBS, one coupler, the other coupler. Fibers, which are connected to longer fiber spools. In our case, that for the simulation, that was 10 kilometers each. We use SSPDs from Scontel. We have to keep them in a cryostat at 2.2 Kelvin in order to get good performance. And we analyze the signal using a scope. So as I said, we use scope as a time tagger in the sense that we have a timing information about the arrival time of each of the photon with respect to the photodiode. And this is actually, these are three different statistics for three different settings of the arrival times on Alice's and Bob's side. So by just tuning the spectral characteristics of the pump, we can switch between positive correlation. Let's say this is almost no correlation. This is close to zero, let's say, like that. And this is the negative correlation. If we feed double Gaussian function to that with this row here, this is our measure of the correlation, of the temporal correlation that we have here in our setup. So I will stick to this setting, because this is the most interesting, because the correlation is the highest. So if, let's say, on Alice's side, we have no information about detection on Bob's side, so then this is the statistics of the photons on Alice's detector. And this is measured with respect to a photodiode. And again, if Bob measures his photons, again with respect to the photodiode, but he has no information about the detection time on Alice's side, then this is his statistics marked with the so experimental result is marked with the blue dots, and theory is fitted with blue line here and here. Okay, so now we have the ability to say when was the count on Alice's side, and actually our timing resolution is of the order of 25 picoseconds. So we can pick only those detections which are around zero here on Alice's side, and those are in the range of 100 picoseconds, just for example. The question is, what would be the statistics of the heralded counts on the Bob side? And actually, that corresponds, this orange range here corresponds to these statistics on the Bob side. So as you see, this guy is more narrow than compared to this guy. And actually, this is that 30% of narrowing that we got. And then we can shift with our detector or with our analysis to 2 nanoseconds. And again, we analyze in the range of 100 picoseconds. And again, the statistics on the Bob side is here. So as you can see, this guy is also more narrow than this guy. And actually, these statistics followed. These statistics followed the heralding time on the Alice's side. So there is a correlation between the heralding, let's say, heralding time and heralded time on Alice's and Bob's side. So let's analyze that. And the question is how narrow the heralded wave packet can be. So we actually changed this range between something a little bit more than 10 nanoseconds to 10 picoseconds. And we analyzed what is the width of these statistics here. So as you can see, so the blue dots correspond to positively correlated photons. And as you can see, it drops to certain value here. And at the beginning, I thought that's the limit, that's limited by the jitter, but that's not, because our jitter is of the order of 25, 26 picoseconds, and here you have like 300 picoseconds. The other thing is that these guys here, this is that middle scenario, which is with let's say almost no correlation, and this is the negative correlation. So again, this is not limited by timing jitter, and actually this limit is given by the correlation. So the stronger the correlation, the deeper this guy goes here. So this is the only limit, and actually it does not really depend on the sign of correlation. Okay, so as I mentioned, this statistic it follows the average detection time on Bob's side. So we can ask how well it can follow. So yeah, what is the what is the average correlation on the Bob's side? So for the positively correlated photon, it is a nice line. So as simple as possible. So this is the positive correlation. So the average detection time of Bob's side on Bob's side follows the average measurement time on Alice's side, and that's similar but opposite for negatively and no correlated photons. Okay, so this scenario can be also used for synchronization of remote clocks, right? Because the precision can be improved using that narrowing effect. And there is my comment about the clock synchronization. There are different alternative scenarios for that. So this is one of the representative paper about that, in which the authors use also SPDC, but this is in a configuration of Mach-Zehnder interferometer. So actually, in this configuration, dispersion is something that is not in favor of this scenario, right? But it can be compensated very well using actually this idea. And in my case, there is no. Actually, what was the difference? There is no need to observe interference, so it might be a little bit more stable, but on the cost of the precision, because whenever you use interferometers, then it's more precise compared to standard, let's say, detection techniques. Okay, so in summary, I showed a way to remotely prepare a narrower wave packet, which can be used, for example, as an application for QKD. So we experimentally show that the narrowing down to 30%, but this is actually not a limit. This is actually what we had in the lab. That's based on the crystal that we have. That can be used for the clock synchronization, and it can improve the distance of standard quantum communication protocols. You can find more in those papers. Those are my sponsors and advertisements. So if you are a postdoc, PhD student, or master student, and so there are some openings in my group. If you are a very young student, of, let's say first up to third year, we organize a summer camp in July, and there are also internships for undergraduate and graduate students at my university. Okay, thank you for your attention.
Time for some questions.
I have a question about this joint arrival times you measured for the photons. even before, yeah, this one. So you have a Gaussian fit to this joint distribution.
Yeah.
So I have like two questions basically. One is the third picture doesn't fit into a Gaussian picture, right?
This one.
Yeah.
Yeah. So in practice, there is a sync function that we have to take into account, but this is just an approximation. So we are looking at how to say the main part of our distribution.
Thank you. Second part is, did it bother you that you have this kind of ripple structure in the density of joint arrival time distributions?
That's natural, because actually we can see that in practice, because those detectors are pretty good in terms of timing resolution. So actually this is good that we can see them, and that also comes nicely from theory. So
yeah, that was my question. Which theory do you have in mind to explain this kind of a picture?
Okay, so you have to take into account the Hamiltonian interaction in SPDC process, and then you have to take into account also coupling and all that stuff. So that model is not analytical in the sense that everything is numerical. So there is no compact form.
But if I have a Hamiltonian, at most I get a wave function. How does that give me this picture which you have measured?
So then you can use that wave function, which is how to say, which is not analytical. So you cannot perform all the integrations by analytical means. So that's why we use that simplified version here.
So
but then, yeah, from that theory, those side lobes they appear.
Okay, maybe we should discuss this further.
Regarding the 30%, is that compatible with the square root of 2? Because
square root of, what does it
1
mean?
over square root of 2, because it looks like it comes from the entanglement between signal and idler pump. We in addition to
this is the consequence of entanglement between signal and idler.
Right.
The stronger
because we had a quantum clock synchronization protocol in which we use the spectral entanglement between photons, and we showed that we get a square root of the number of photons and increase in the resolution of the timing. So I'm wondering if this
but this is in the photon number, right?
Yes.
So here you have just 2 photons. So this is a different scenario.
2 photons, so you have a square root of 2.
Okay, so you're asking if this is below that limit.
Right.
I'm not sure. I will have to check.
This effect.
No, not really, because it can't be that limit, because that narrowing is given from theory, is given by this relation. So the heralded to non-heralded width is given by square root of 1 minus correlation, and it comes from the theory. So I believe this is a little bit different scenario. We can discuss. I'll be happy to discuss that with you.
Thank you.
And then finally, there was one question, right? Sorry, no problem.
No, I'm a little confused. In quantum mechanics, I mean, I suppose you're using quantum mechanical theory.
Okay.
How do you define time of arrival? Because time is not a dynamical operator. I mean, it's not an operator which is measurable.
That's a good question. So, what do I define? Actually, in practice, I observe my instruments. So in practice, I observe my instruments. I have a photodiode, and I have a single photon detector. And in the end, I have electric pulse, which I measure with another instrument, which is oscilloscope. And this is my time of arrival. So I don't have anything else.
It's empirically done. That's what I'm asking.
Excuse me?
It is empirically determined.
Yeah. So there is no sophisticated definition about the time.
That was the nature of my question. What theory did you use to reconcile this measurement? And then you said that you don't have the wave.
Okay, so at the beginning you have a wave function which is in a spectral domain, and then you can Fourier transform to the time domain. That's it. So if you have Hamiltonian, then you get a wave function which is parametrized by something. In this case, spectrum.
These times of the Fourier transform
Yeah, this is a perfect match between these two.
I may just add a remark because I've worked personally on this arrival time question in non-relativistic quantum mechanics. There is a whole literature on arrival time distribution within non-relativistic quantum mechanics, how best one can define in terms of having some prescriptions either in terms of current density, appropriately consistent. And there have been some discussions that about the photons, what you do, though strictly you would require relativistic equation for photons, but still with non-relativistic quantum mechanics, the kind of formalism done with current density, it is possible to map it to the photon case, and then what you do, some sort of justification for that can be built up.
Yeah, so in practice, at the beginning we have, okay, so in the other words, how do we marry practice and theory, right?
Yeah.
So from the theory, as I said, at the beginning we have a wave function which is parameterized with a frequencies of signal and Tyler photons, and then we Fourier transform that. We got variables which we call time, and it happens to match what I measure.
So still there is some rigorous here lacking, but there is sufficient to work on it. But even in non-relativistic quantum mechanics, it's a problematic area.
Can be.
Okay, so thank you very much. Let's thank the speaker one more time.